Hello all. This video will be a brief introduction to the process of downdraft gasification. It will also discuss some of the current applications, potential for future growth, and some of the inherent limitations of the system. I hope you enjoy. Before we get started, I'd like to give you a brief overview of the points that will be discussed in this video. We'll start with the general introduction into the downdraft gasification process, and then we'll discuss a more technical overview of how a system like this might function. Then we'll discuss some inherent capabilities and limitations of gasification technology, and that will lead us into discussion of some current applications and then the potential for growth of this technology. And after we've covered all those points, we'll do a little recap and we'll draw some conclusions from the things we've discussed. Downdraft gasification is the process of reacting organic or fossil fuels at high temperatures without combusting them. This is done by regulating the amount of air or steam that is allowed into the process. And this reaction will produce syngas, short for synthesis gas, and you may also hear it called producer gas. It consists primarily of carbon monoxide, hydrogen, and carbon dioxide. Syngas can be burned directly in any spark ignition internal combustion engine, but it may also be used to synthesize many other desirable compounds, such as plastics or synthetic fuels. Downdraft gasification works primarily by employing a process called pyrolysis. Pyrolysis is a high-temperature decomposition reaction that involves a simultaneous change in phase and chemical composition of a substance, and this occurs in the presence of little or no oxygen. A simpler way to think of this might be as a reassociation of chemical bonds. That is to say that a feedstock material, which is comprised primarily of carbon, hydrogen, and oxygen, undergoes a reassociation of its chemical bonds at high temperatures to produce a gas that is primarily carbon dioxide, hydrogen, and carbon monoxide. This is called syngas. In addition to syngas, this reaction also produces some sort of ash. In the case of biomass gasification, this is biochar, a high carbon substance which is valuable to agricultural industries. In the case of coal gasification, slag is produced as well as syngas, and this slag can be used in road construction. Downdraft gasification offers a cleaner way to produce energy than traditional combustion of fuels, and it may even be renewable and carbon negative depending on the feedstock that is gasified. The syngas produced by this reaction has the ability to be combusted directly in any internal combustion spark ignition engine to produce energy. It also has the ability to be synthesized into many other desirable compounds. However, there are some drawbacks or limitations. This gasification reaction takes time to bring up to steady state, and depending on the feedstock material that is used, a complex design might be required in order to achieve the purest syngas possible, depending on tar contents. This reaction also may not be throttled quickly to meet changing loads or demands. The capabilities and limitations presented lead us directly into a discussion of current applications. At present, there are several facilities throughout the world that employ downdraft gasification technology to produce power. In my home state of Tennessee, the waste-to-energy plant processes approximately 64 metric tons of waste per day from surrounding industrial ventures to produce electricity, and it is projected to power approximately 350 homes per year. The international power company CEZ has a downdraft gasification plant in Bulgaria, which uses refuse from local wood processing operations to produce approximately 4.5 megawatts of power. This power is 2 megawatts of electrical energy and 2.5 megawatts of waste heat. This waste heat energy can be used for local heating needs or to dry the feedstock if it becomes excessively wet. Mobile vehicular platforms have also been constructed to power internal combustion engines with on-board downdraft gasification. Though this technology has been proven and can be done, it is inherently wasteful. This is because the gasification reaction cannot be throttled to meet the changing needs of an engine. As you may know, an engine does not achieve its full power during most of its operation. This means that a gasification plant that is designed to produce enough syngas to meet the full needs of the engine is wasting syngas during most of the vehicle's operation. However, a plant that is designed to produce a lesser amount of syngas may run the risk of underpowering the vehicle. Current gasification plants have been most successful when they convert industrial waste into energy. As this technology grows and gains more recognition, so does the possibility for industrial partnerships. This means more clean energy that can be produced and less material that must be landfilled. Small-scale gasification plants have also been investigated, and they would convert biomass waste to energy on what has been called a farm scale. The most important factor for the success of a biomass plant is a steady supply of a feedstock whose chemical properties are known. To recap the points that have been discussed, gasification employs a high-temperature decomposition reaction to produce syngas, which is high in carbon monoxide, hydrogen, and carbon dioxide. And this syngas can be used to generate energy directly or can be synthesized into many other desirable products. This process can be both renewable and carbon negative depending on the feedstock material that is gasified, and it is most successful when employed with steady state operation.